Hello there, this is exercise 10a looking at sine and cosine graphs. Of course, we've seen the sine and cosine ratios in the past when we've looked at SOHCAHTOA and similar things. But today I want to look at a bit more than just the ratios and actually look at what happens if you want to find, I don't know, the sine of, say, 200 degrees rather than 48 degrees. Up till now, we've limited ourselves to smaller angles, and theoretically it could be 700 degrees put in, which is a bit weird really. Actually on the screen there we've got a graph which is similar to a cos graph, but it's not quite a cos graph. That little starter anyway. Find without using a calculator. A lot of stuff we have to use without a calculator, and there are reasons for that later on. But it says find the exact values of sine x and tan x if we know that cos x is 4 over root 31. Now look, this is really, and it does give us a hint, draw a right angled triangle, might help. So if you get this kind of question, what you're doing is, let's draw a right angled triangle like it tells me. And it says cos x, so x is the angle, so I need to put the x somewhere, it might as well be there. And cos x, of course, is 4 over root 31. But you might remember this SOHCAHTOA rule. SOHCAHTOA says that, for instance, cos is adjacent over the hypotenuse. So this is the adjacent, and this is the hypotenuse. And effectively on my triangle I can therefore say the adjacent must be 4, and my hypotenuse is root 31, or that's nearly put it in the wrong place. Now, by Pythagoras, I know that, well, it depends what you want to call it, probably b squared equals, usually you call it the c squared, which is the big one, minus the little one, a squared. So in this particular case, if I want to find this opposite side, which I'll call b squared is the hypotenuse squared, and it's root 31, so if I square that, you should see that as 31, minus a squared, well, 4 squared, now I do have to square that one, that hasn't got a square root, so that's 16, and 31 minus 16 is 15, so therefore the b, the opposite, must be root 15, because b squared is 15. How does this help? Well, sine is opposite over hypotenuse. Opposite over hypotenuse. So sine x is the opposite, root 15, divided by the hypotenuse. Now that's probably better written as root 15 over 31, and some people won't even like, that's over all of it. Some people don't like the 31 being on the top being rooted. You know, this is this idea of rationalising the denominator. But you've got a calculator to work this out for you. Or you could just quite easily do it yourself. If you times top and bottom by root 31, then the top becomes, what's that? 31 times 15. I'll let you use a calculator for that. 465. So it becomes root 465 over 31. But to be honest, this one's good enough as well. I wouldn't worry too much about that. Tan x, what have I got for tan x? Well, tan x is opposite over adjacent. What was the opposite? Oh, is that what I found first of all? Opposite over adjacent. Oh, right, I nearly made a mistake there. It's root 15 over 4. Or again, you could write that as a quarter of root 15. Some people prefer it like that. So what did I write my answers as? I didn't write it as anything. There you go. So that's the answers. Now look, this is the sine of any angle. I've got to adjust this slightly. The one problem they've got with this is measured in something called radians, which we come up to later. But as far as we're concerned, this is 180 degrees. And this over here is 360 degrees. So likewise, this is 90, 180. This is 270. If you go further, you get to 450. And it keeps going. And in actual fact, it goes to the left as well. So you could draw this graph down here. And it keeps going, so you could draw this graph up here, and you know, it just keeps on going and going and going. It doesn't stop ever for any value. So this is the graph of the sine of any angle, and you see this actually at GCSE. I'll point out this is called the cast diagram. The idea of the cast diagram is it starts at 0 degrees it goes to 90 degrees, it goes to 180, it just goes round in a circle. That's 270. Eventually you get back to 360. Now this is called, from 0 to 90 as it goes round, this is called the first quadrant. This is called the second quadrant. This is the third quadrant, and this is the fourth. But we'll come back to that in a bit. I suppose really what I'm after on this exercise is that you get the shape of the sine graph. This is y equals the sine of x. Okay, that's really what I want you to know. Notice it goes up to 1, it goes down to -1. It doesn't go beyond those points. Now this then is a similar idea, the cosine graph. We've still got the cast diagram, and ignore that again. Just be aware it carries on going forever and ever, so it kind of does this up there, and when it gets up to here it starts coming down again. In terms of angles, this is again 90 degrees, 180 degrees, 270 degrees, 360 degrees. We'll have 450 degrees over here, and again 0 and -90 also apply. Now it still goes up to 1 and -1, but it kind of starts in a different place. We describe it in physics as a phase shift. It's sort of slid over. In mathematics we call it a translation. Just one thing's just been translated to the other. So on that basis, let's just talk about a few more features of the graphs. The distance from the middle of the graph to the top of the graph is called the amplitude, and it's tempting to think of the amplitude as from top to bottom. It's not that. It's, you find roughly where its middle point is, and you say how high does it go from there, how low does it go from there. So you'll notice the amplitude of this graph is 1. It goes from 0 up to 1. And the period is you pick a point and you look for an equivalent point. So here it's the point where it's going upwards at 0, and here it's going upwards at 0 again. And so the distance between there and there is 360 degrees. So here the period would be 360. It's not just where it gets back to 0 again. That's not the period. The period is when it completes one complete cycle. Okay, so 360 here, and in this case the amplitude is 1. So these are some trigonometric rules, and by this I mean that there are a variety of values. So for instance, I'm looking at that value there. Now I know that that is 30 degrees, but it's not the only place where it hits there. Notice it hits, by the way, at 0.5. There are other places where it hits. There's one. That, as in a matter of interest, is 150. And it's the symmetry of the graph that tells me that. That's 30 degrees to that point from the 0. So from the 180 we go 30 back again. And you get a variety of these where the symmetry of the graph gives us lots of different places. So before I go on to cos, there are a couple of rules then. One that we've just seen. One says that the sine of 180 minus x. So for instance, in that case I said the sine of 180 minus 30, which is of course sine 150, and I'm saying to you, if you type it into your calculator, you get the sine if you type, same as if you type in sine of 30, and the graph tells me that. But I can also add on 180, so the sine of 180, so take that point there, 30, if I add 180 onto that, I get up to the number 210. So if I go from 30 and I add on 180, you'll notice it's a similar scenario. It's meant to hit there, actually, if I drew it properly. So I can say, for instance, that the sine of 210 is equal to minus the sine of 30, because this equation here says it will be a minus this time. And it is, allowing for my dodgy graph, it hits at minus 0.5. Here's another rule, and it basically says if you add on 360, so if I go to 390 for instance, you'll notice you just basically get another point where it's equal to 0.5, and that always works. If you add on 360, it's the same place. And the last rule says, so the example of this, by the way, would be sine of 390 is equal to sine of 30. And the last one is basically, if I go to minus 30 instead, and I go down in this case, you'll notice it hits at minus 0.5. So sine of minus 30 is minus the sine of 30. And that's what those rules tell me. I've got similar rules for cosine. Again, notice one of them is exactly the same. If you add on 360, you get the same answer. So cos of some value, I'll pick 60 this time. Cos of 60, if you do cos of 60, the reason why I pick cos of 60 because I know that's equal to 0.5 again. It's a nice answer. So 60 there. If I add 360 on, 360 at 360 is 420. Now 420 is about there. And I reckon that's there. So you can see this works. Adding on 360 always makes it the same. But some of the other rules are different. So just take a bit of time and go through those differences. But these rules, it's useful if you remember them. So for instance, on this question, this is a sine question, sine of 152. The one thing I've been told is that sine 28 is 0.47. If you do it, type it in your calculator, you'll get that. Now, which rule does it look like? Now, it looks to me like this rule on the first one. I'm doing sine of 180 minus a 28, and that's obviously sine of 152. And the rule says it's the same thing. So I think this is 0.47. Doesn't change. You can look up there, 152, something like there. 0.47, oh, so it must be about there actually, if I do it accurately, and then, and the idea being you get the same answer. Sine 388, oh, well I reckon that is just, I've added on, I've started with a 28 and I've added on 360. That's what 388 is. And using this rule tells me that doesn't change, it's still 0.47. Again, type it in your calculator if you want to check, but it will work. What am I doing on this one? How do I get 208? Well, I reckon to do that, I do sine, and I use this rule now. I do the 28, but I don't add on 360 this time, I add on 180. And what's it say it gives me? It says it gives me minus the answer I had before, so it must be minus 0.47. Again, type in sine 208 in your calculator, it'll give you minus 0.47. So this is why I think these rules are really useful. Good, Eva agrees. What's it say here? It says cos of 113. How do I get 113? Well, it tells me that cos of 67 is this. I reckon this is cos of 180 minus the 67. What do I do? What's that? Ah, that gives me, the rule says it's minus the answer. So this is minus, well, it was 0.39, so it's now minus 0.39. Cos of 427. Well, that sounds to me like cos of, it's this one. I could take my 67 and I add 360 on. That will give me 427. So really you're just playing around with ways to make the number you get. Now what's it giving me? It says that's the same as cos x. So cos x, well, it was 0.39, so it's still 0.39, no negative involved. It'll either be positive or negative version of what they started with. How do I get 293? Well, again, I reckon this is 360 minus 67. Yeah, that works. What's that rule say? Oh, it says if you do 360 minus it, it's the same as what it was at the start. So this is, what was it, 0.39. Yeah. Okay, so on this example, what we've got is a slightly more complicated one. So I've got A here. I know that cos of 61 equals that. So I suppose, what can I do to the 61 to find a cos of minus 241? Well, I think it's a double trick actually. I'm going to add on 180. This is not the number I want. I can work out the cos of 241. And over here, where does it say? If I add on 180, I get the minus version. That's what that says. So that will give me minus 0.484 because I know that cos of 61 was that. But the trick is, if I then want to make minus 241, it will be cos of that is the same as the cos of x. So this cos of 241 was this. I think it's still minus 0.484. B, I think, is a similar trick. I know that sine of 125 is this 0.189. If I add 360 onto this, this will give me sine of 485. Sine of 485, I've added 360, it doesn't change it, it's over here somewhere. So this is still 0.819. Critically, if you change the sign now to 485, again, use your rule, it says this becomes minus 0.819. Yes, they were right. So look, exercises, exercise 10A. Have a look at those. I've got the rules for you there to help you. So best of luck.